So hello everyone, welcome to the second part of lecture number 34. So in today's lecture we will be continue our discussion on MOSFET capacitance. MOSFET capacitance. So basically if you have seen, MOSFET capacitance are divided into two parts, which is junction capacitance and oxide related capacitance. So under junction capacitance, let me show it to you in the structure itself. So this is my MOSFET structure. This is my gate material made up of metal or polysilicon. This is my gate. This is my oxide layer, and I have my N plus source and N plus drain diffusion regions. Alright, and here is my P silicon substrate. Okay, now as informed earlier, these are junction capacitances, so these are related to the PN junction. So there is two more layers which are present. This is P plus. This is actually channel stop implant. This is source. This is body, and this is your drain terminal. And this again, this P plus region is a channel stop implant to prevent the formation of any illegal channel formed between adjacent MOSFET and the same substrate. Alright, so which are the PN junctions formed over here? This is PN plus junction. So here we have capacitance which is called as CSBJ, okay, source to substrate junction capacitance. And we have one more over here, drain to substrate junction capacitance. Okay, so these two are area capacitances. Okay, so CSBJ and CDBJ are area capacitance with the unit of farad per centimeter square. So these are area capacitances. Alright, so and we have to derive its expression, uh, you know since it is a junction capacitance, we have to arrive at the expression for these capacitances CSBJ, CDBJ. And there are actually one more type, sidewall capacitance. Sidewall capacitance. There is another PN junction over here. So let me show it to you. But this is around the periphery. So there is one more PN junction. So this PN junction is called as CSWSJ. Okay. This is source to substrate. I mean sidewall capacitance. And there is another PN junction over here. This is CSWDJ. Okay, drain to substrate sidewall capacitance. Okay, so this is sidewall capacitances are CSWSJ, CSWDJ. Now they are not area capacitances. We know we will, when the time comes, I'll let you know why they are not area, and their unit will be farad per centimeter. Okay, all right. So now let us continue. I guess I have to admit someone. It's better that you all join via my email ID, but it's okay. Okay, all right. So you have understood we have to derive the expression for the next 20 minutes or so for these four capacitances. These two area capacitances, CSBJ, CDBJ, and this is sidewall capacitance, CSW, that is sidewall SJ, CSW DJ. Okay, whose unit is farad per centimeter. We'll see why its unit is farad per centimeter. Alright, so are we ready to start? For this I will use one of my older PDFs where these derivations are already available. So this is that PDF. Okay, so let us use this PDF in deriving because the derivation will take a lot of time. So hence I am using this PDF. Let me say if I can write over here. Okay, yeah. So junction capacitances, first our focus is for deriving the expression for voltage dependent. These two, I mean all the four which we have discussed are voltage dependent. Okay, so these are voltage dependent source to substrate and drain to substrate junction capacitance. Alright, so what is the origin? They are due to the depletion charge surrounding the respective source and drain diffusion regions. Now as you can see over here, there is a PN junction formed, right? Now inside this PN junction, we always draw a depletion layer like this. If no channel is formed, the depletion layer will be like this, surrounding the channel. Now why this depletion layer is formed? Because of the same reason, it's a PN junction. Okay, and this depletion region will keep on widening if I increase the reverse bias voltage applied to these terminals. Yes or no? So that is the origin of these charges. This is my depletion layer. So in a PN junction also, these charges are present in reverse bias because of the change in the reverse voltage and because of the change in the depletion layer. So that's the origin. So both uh, source substrate, that is N plus P and N plus P junctions, are reverse bias under normal operating conditions. Now why they are reverse bias, let me show it to you over here. Normally drain voltage we apply positive, right? Now we apply this positive with respect to the source terminal. This is negative. Yes or no? And the body normally is connected same as your source terminal. So this is normally grounded. Okay, sometimes if VSB is not equal to 0, that means our source to substrate bias is not equal to 0, and this is, for this case, your threshold voltage becomes VT instead of VTO. So here we applied a positive potential. So when we apply positive potential to the N plus region and negative to the or negative to the P silicon substrate, then we call it as a reverse bias because we are reverse biasing this diode. Similarly, in the source to substrate, when VSB is not equal to 0, we are reverse biasing it. We normally apply VSB as positive, so this is positive, this is negative. So you apply positive to N plus, negative to P plus. Okay, so this is the way we can apply. We can say that we have reverse biased this, junctions. So here, yeah, both source substrate and drain substrate junctions are reverse bias. That is the meaning of it, reverse bias, under normal operating conditions of the MOSFET. So the area of the junction capacitance is a function of applied terminal voltage. Okay. Now, this is, let's say, a little bit sidetrack, but this is required. Sidetrack in the sense we will be indirectly finding the depletion capacitance or the junction capacitance inside a PN junction diode, inside a basically reverse bias PN junction diode, and then we'll apply this to the uh, in our case. So assume that the abrupt doping profile with a constant doping density Na and Nd are there for the N and P side. Nd, not Nb. This is Nd. So this P side is made up of doping as Na. N side we have a doping Nd, and this is my depletion layer. So depletion layer thickness is XD. Okay, and V is my applied reverse voltage, as you can see very clearly. Alright, so we will be deriving the capacitance for a normal PN junction, and then we'll apply to our case in case of MOSFET. So the built-in barrier potential in a reverse bias PN junction, it's a standard form, we don't need to derive it. It's given by phi naught is equal to KT by Q natural log of NAND upon Ni square. So this is our equation number 1. Now where this came from, we don't have the derivation for it. You remember we have derived the expressions for phi Fn and phi Fp for this side and this side, right? We have applied Fermi potential for the P side and Fermi potential for the N side, and we have said that total Fermi potential will be the work function difference between the two different materials, right? P side and N side, and that was found to be around zero point 0.7. Okay, so somewhere related to that, but since there is a depletion layer present over here, there are charges present, and whenever there is a charges present, there will be a presence of an electric field because of the built-in potential. So here we have a total built-in potential as negative to positive this way. So there will be electric field directed. So this depletion region charge or potential is called as phi naught, KT by Q ln of natural log of Na Nd upon Ni square. So this is a step number 1. Now depletion region thickness is given by this formula. You remember depletion region thickness of either we have derived it, right? So what was the formula for us? It was square root of twice epsilon for silicon divided by Q. Okay, and I think we have written as Na and D, Na into phi naught. This was the formula, right? I think Q Na was down, if I am not mistaken.
Yes, sir.
right? So this was the derivation for XD. Now we are applying to Na and Nd both. Now this depletion region thickness is for both PN junction. So here, and also this voltage has to overcome the reverse bias voltage. Okay, so this will be phi naught minus V. Alright, so this barrier potential minus this applied voltage will be XD. Actually, this will be mod actually, because this term will be negative. The square root of a negative number is not defined, so this will be a mod actually. So it will be xd will be twice epsilon of silicon divided by q into 1 upon Na plus 1 upon Nd into mod of phi naught minus V, which is the applied reverse voltage. Alright, so xd depletion region will be your in centimeters, so it's a length. So xd will be square root of twice epsilon silicon upon q Na plus Nd upon Na into mod of phi naught minus V centimeter. So this is equation number 2 of the derivation. Then depletion region charge Qj. So how much is the charge? Now we are finding out how much will be the charge on this depletion layer present. This is, we are calling it as Qj as a function of voltage. So we are calling it as a junction charge or depletion region charge Qj. So tell me how much it will be. Obviously it will be multiplied with the area. Okay, charge is how do we define the charge? Anyone? Yeah, Q depletion region charge. So here we are multiplied with the area, the Q, the charge on the on the and Na Nd upon Na plus Nd into xd. So this is in coulomb. So this is the A is the periphery area of the junction. Q is the charge on the electron. Then Na Nd upon Na plus Nd into xd. Now this xd from formula number 2 we substituted over here. Okay. Yeah, this we have derived it for the MOSFET earlier. Yeah. So here, yeah, let me concentrate over here now. So A into Q into Na Nd upon Na plus Nd into xd. So this we have rewritten the expression. This is mod actually. Again, I am representing this as a mod. Okay. So we have multiplied this. Now, if I want to consider this Na Nd upon Na plus Nd inside, so if it goes inside, it becomes multiplication, right? Inside it will become Na square Nd square upon Na plus Nd the whole square. So we get over here, the formula will become as Qj of V is a function of reverse voltage, A into square root of twice epsilon of silicon into Q, because Q also inside it goes Q square, so it will be Q Na Nd upon Na plus Nd into mod of phi naught minus V, and that is in coulomb. So do we get this equation number 3? Okay, yes or no? Are you following up till now? Okay. Now, the capacitance, junction capacitance is a function of voltage, is defined as rate of change of discharge. Okay, dV by dq by dV. Okay, normally we write dq as C dV, right? Rate of change of charge will be with respect to capacitance, which is a constant, with respect to rate of change of voltage. So dq C will be Cj of V will be dq J of V upon dV. Okay, mod of it. So we have to differentiate equation number 3 with respect to dV. So when we differentiate equation number 3 with respect to bias voltage V, which is a reverse voltage right now, so hence we consider this as a mod again. So differentiate it with respect to V, what do we get? So this term will be a constant. Okay, so differentiation of this will be A square root of twice Q epsilon of silicon Na Nd upon Na plus Nd divided by twice square root of phi naught minus V. You understanding? Yeah. So it's basically x raised to half. So what it will be? Half into x raised to minus half. Yes or no? So minus half we can write it as 1 upon square root of x. So that is what we have written over here. Half square root of x. This is differentiation. Let me let me rub this out. Okay. So that is what we have done. Now what we are doing is we are taking phi naught out. So if I take phi naught out, it becomes phi naught square. So inside you will get 1 minus v upon phi naught. That is what we have done here. Only change here. Okay. So now, if I divide phi naught by numerator and denominator, if I take this in the numerator term, now what will I get? If it goes phi naught, if it goes inside the square bracket, it will become phi naught. Not phi naught square becomes phi naught. Okay, and this 2 also, if I take it inside, it will become here it was multiplied by 2, here it will become divide. So this is the formula we get. Cj of V is area times square root of Q epsilon of silicon Na upon Na plus Nt divided by twice phi naught divided by square root of 1 minus V upon phi naught. This, please write this expression which is written in the box. This is equation number 5 and it is in farad. The unit is in farad now so far. Okay, so this is very important for solving of numericals. So Cj of V will be, is a function of voltage, will be area into square root of this term in the numerator, and denominator we have 1 minus V upon phi naught. Okay, A is my junction area, and if I rewrite the same expression, if I rewrite equation number 5 as follows: Cj of V A into Cj0. So Cj0 is basically zero bias junction capacitance per unit area. See, this is zero bias junction capacitance, this one. So this we are calling it as another term Cj0. Okay, zero bias. Zero bias capacitance are already available, right? And it will be 1 minus V upon phi naught raised to m, where m is a grading coefficient. It is half for abrupt junction and 1 by third for linear graded profile. Okay. Abrupt junction meaning that if I have a PN junction like this, PNN, my doping profile over here changes abruptly. So let's say it was Na over here, it abruptly changes to Nd like this. So this is what you call as a step or a abrupt junction profile. Alright, so that's why we take it as a half. If we take m as half, then we'll get back this original equation number 5. So please write down equation number 6 also. The unit will be farad. And Cj0 we don't have the area term, so unit of Cj0 will be farad per centimeter square. So write equation number 5, 6 and 7. Please note down equation number 5, 6 and 7. And Cj0 is called as zero bias junction capacitance per unit area. Okay. When you have completed, let me know. Have you completed writing 3 expressions? 5, 6 and 7? Yes or no? So let me know. Please write them one by one. Cj of V will be junction capacitance as a unit of bias voltage. We have written in a concise form, and Cj0 is zero bias junction capacitance per unit area. Have you completed writing this?
Yes, sir.
Okay. Now we are considering abrupt or junction profile. So Cj of V in our case will be A into Cj0 divided by 1 minus V upon phi naught into half. Okay. So this we get equation number 8. Now, so therefore we can say that your junction capacitance depends upon external bias voltage V that is applied across the PN junction. Yes or no? So in our case, okay, so we have written as CSBJ equal to A into CJ0. Now here let me say, this will come back to it later. We will come back to this formula later, area capacitance formula. But here this expression number 8 shows that your junction capacitance is a function of bias voltage, external bias voltage V. So we'll come back to this. We have derived these expressions. Now let me derive the expressions for large signal equivalent junction capacitance. Okay. So what are we assuming now? We are assuming that the terminal voltages of the MOSFET changes during the MOSFET operation. So we have a MOSFET over here. Okay. This is N plus source, N plus drain, and we have gate terminal over here. So this is my gate terminal. This is P silicon substrate. Let me mark the gate terminals. This is my gate. This is my source and drain terminal. So we are saying that the terminal voltages changes during the dynamic operation of the MOSFET. So we are finding CJ equivalent junction capacitance. Okay, large signal equivalent junction capacitance. So we are estimating the junction capacitance under varying bias conditions. So let's say my reverse bias voltage VDS, which we apply, is changing from 1 volt to 2 volt. So this is large signal change. It's not a small signal change. Normally we apply 1 volt incremental change, 0.01 and so. But right now we are changing, VDS is changing from 1 to 2 volt, which is a large signal change. Okay. So we will calculate the large signal average junction capacitance over the range of voltages. So we are estimating if my, let's for example VDS is changing from 1 volt to 2 volt, what will be my CJ equivalent, large signal equivalent change responding to. It is also a function of voltage. VDS is my reverse bias voltage for this, for these PN junctions, right? For these PN junctions it's a reverse bias voltage. Okay, so how is my capacitance reacting to it, because it is dq by dv, right? Now if dv is changing such due to such a large amount, then obviously the capacitance also will change, and that is why we are estimating cj equivalent. So cj equivalent will be dq by delta q by delta v. So it will be qj of v2 minus qj of v1, v2 minus v1. So let's say that instead of 1 and 2, we are talking about the voltage which is changing from, let's say, 0 to 5. Okay, so in this case, in our example, what it will be? It will be qj of phi. V2 is the final voltage. Vj qj 0. Then it will be phi minus 0. Are you understanding? This is an example which I am given. So let's say the reverse voltage is assumed to change from V1 to V2. Alright, so V1 is 0. Oh, and V2 is phi. So here it is the charge associated with the voltage phi, charge associated with the voltage 0. Okay, so that will be delta q by delta v. So cj equivalent is calculated for a transition between two known voltages. I mean, we know this, the change in the voltage, so we know the value of v1. Let's say for example it is 0. We know the value of v2, so these are known voltages. Okay, so if we want to find the capacitance, we will integrate with respect to the area, because this is a known quantity, it is a constant, we know it, so that's why we have taken out of the integration, and we are integrated over from v1 to v2. And if we calculate cj of v, we know this is junction capacitance for a reverse bias, we will get equivalent junction capacitance cj equivalent of v. Understood this? Yeah, so cj equivalent of v will be 1 upon v2 minus v1 integral of v1 to v2 and cj of v dv. Yes, can we start? Did you understand this statement?
Yes, sir.
Okay, so from equation number 6, what is cj of v? Cj of v was a into cj0 divided by 1 minus v upon phi naught. General expression was raised to m. At the end we'll substitute m equal to half, not now. So right now let us as it is. So this we have substituted over here. So out of this a cj of 0 is a constant, so we take it out. Here it is. Take it outside the integral. So we get cj equivalent of v will be a into cj of 0 upon v2 minus v1. So integral v1 to v2 1 minus v upon phi naught raised to minus m. This we have written it at the top, dv. So what's the integration of x raised to minus m? Hello? What is this integral? Anyone remembers? x raised to minus m plus 1 divided by minus m, right? So that is what we get. So 1 minus v upon phi naught minus m plus 1 divided by 1 minus m minus 1 by phi naught. That is what we get as a integral for this integration with limits v1 to v2. And now from here we substitute v1 and v2 one by one. Okay, so 1 minus m, here it is a constant. This minus of 1 upon phi naught will come out over here. So minus a cj of 0 phi naught divided by v2 minus v1, 1 minus m, outside it will come, and inside the bracket will v will change from v1 and v2. So it will be 1 minus v2 upon phi naught raised to 1 minus m, and minus of 1 minus v1 upon phi naught raised to 1 minus m. Understood this? And for abrupt p-n junction we substitute m as half. So we got the value of cj equivalent of v as minus twice phi naught a cj 0 v2 minus v1 square root of, because m becomes half, so it is 1 minus half, which is half, and here it is minus of 1 minus half, so again it is half, so half means square root of. So therefore we get this term. So we have to write down these terms. Okay, so be ready to write it down. So cj equivalent will be given by this expression minus 2, because m is half, so 1 minus half will be half, that 2 will come over here, phi naught a cj 0 v2 minus v1 into bracket square root of 1 minus v2 upon phi naught minus 1 minus v1 upon phi naught, which is equation number 9. Okay, so now this equation we are calling it as k equivalent. No, not this equation actually. This expression, entire expression. Let's see this expression. This entire expression we are calling it as k equivalent. We are calling it as a new term, k equivalent. So cj equivalent of v will be k equivalent into a into cj 0. Okay, so this is my k equivalent term, cj equivalent term, and k equivalent is a dimensionless quantity. The advantage is its unit is, I mean, its value is between 0 to 1 always. So it will be minus twice phi naught v2 minus v1 divided by v2 minus v1 into square root of 1 minus v2 upon phi naught minus square root of 1 minus v1 upon phi naught. Okay, it is called as a voltage equivalence factor. It allows us to take into account the voltage dependent variations of the junction capacitances. So this k equivalent term is dependent upon the change in the bias voltages. It takes into account that. Okay, understood? So write equation number 9, 10 and 11 please. I'll give you some time. Please write down equation number 9, 10 and 11. Written? Okay, keep on writing the equation number 9, 10 and 11, because what we are going to discuss in next 5 minutes is as important as discussing the derivation. When you have completed, let me know. Cj equivalent of v in terms of k equivalent, where k equivalent is this formula, and it's easier to find k equivalent, and its value can be confirmed between 0 to 1, of course modulus of it. So mod of k equivalent actually. Okay, voltage equivalent factor. So let me know if you have completed this. Completed, yes or no? Write down expression number 9, 10 and 11.
Yes, sir. Complete.
Okay, now comes the very important thing. During switching, junction capacitance increases from its original value by, let's say, plus or minus 5%. So let's say it was around 100 picofarad, it increases to 105 picofarad or 95 picofarad. So this much variation is allowed during switching. Okay, Fine. So we will now analyze this geometry. Now very important from the numerical point of view. Pay complete attention now. Okay. We know that this is my channel, right, between n plus diffusion region. This is n plus drain diffusion region. This is n plus source diffusion region. Okay, this is n plus channel and n plus. This is my gate. Okay, and this is my gate oxide. This is my gate oxide actually, and on the top of it I have my gate like this, and I take the terminals out. I am not drawing it properly, but here it is a 2D structure. You can imagine here up above it which way gate terminal. Okay, now check the dimensions very carefully. We have marked here. This is my channel width. Okay, where is my channel length? Can you tell me? Where is my channel length? Channel length is between this and this. Agree? This is channel length L. This is channel width W. Understanding? Acha, what is Y? This is the three-dimensional view of n plus diffusion region within the p-type substrate. So here below we have all p-type substrate. Okay. What is xj? What is xj? Remember we have drawing this p-n junction from since long. I mean this substrate. So the depth of this substrate is my xj. Depth of this junction is called as xj. Are you understanding? Yes or no? So this is xj, this is w. What is y? We have written that initially. What is y called as? This is the diffusion region ka length. The length of the diffusion region is called as y. Alright. What is w? W is the channel width. L is my channel length. Y is my this diffusion region length. Alright. And xj is my depth of this channel of this n plus source and diffusion regions. Do you understand the geometry here? So it shows, this diagram shows a partial geometry of a typical n channel enhancement MOSFET focusing on n type diffusion region within the p type silicon. So we are basically focusing on over here. So we have written over there, see 1, 2, 3, 4. These are all side walls. Yes or no? And 5 is bottom area. Understanding? 1, 2, 3, 4. These are side wall. These are side of this two-dimensional box, rectangular box. If I hope you can imagine. Okay. So let's start. No need to draw this. Just listen carefully. The n plus diffusion region. This is my n plus diffusion region, right? Drain diffusion or both the n plus diffusion regions forms a number of planar p-n junctions with the surrounding p silicon substrate. So how many p-n junction they form? So see here, if I can show over here with the blue color, below we have p silicon. Okay, so here we have entirely in the vicinity p silicon substrate. You can imagine, and on the bottom side, on the right hand side of this, we have what? We have p plus channel implant, and here we have again a p plus channel implant. Yes or no? So this is p silicon and this is p plus. We draw over here, na? Here p plus channel implant. Yes or no? So this is what the situation is. This is p plus, this is p plus, this is p silicon. The n plus diffusion region forms number of planar p-n junctions with the surrounding p substrate. So this is p substrate, right? So all of them 1, 2, 3, 4, 5. All of them form a p-n junction. Yes or no? Because this is made up of n plus and this is p silicon. Yes? Agree? Now what are the dimensions? What are the dimensions of this rectangular box? The dimensions are W is the width, Y is the diffusion region width, and Xj is my depth. Okay. So out of these 5 planar junctions, 2, 3 and 4. See, planar junction number 2, 3 and 4 are surrounded by P plus channel stop implant. Did you get it? No.
Yes, sir, got it.
How? This is N plus is surrounded by P plus channel stop implant. How? Explain how. Out of 1, 2, 3, 4, 5, 2, 3 and 4 are surrounded by channel stop implant. The reason being that, let me show it to you. So here I have my N plus region, drain region, right? And now in 1D view we show it like this. And in the cross sectional view P plus. Yes or no? Now this channel is like this. This channel formed is like this, right? See this way. So it will be surrounded by all the three sides like this. Can you imagine? So that's why which are the capacitance which are affected? 2, 3 and 4. I hope you are getting, can you visualize now? Yes or no? 2, 3 and 4 are surrounded by P plus channel stop implant. Okay. And what are the, I mean, other regions surrounded by? So 2, 3 and 4, it's making a PN junction as, making a PN junction with P plus N plus junction. This is 2, 3 and 4 with the side wall. Yes or no? Agree? So they are making a PN junction with P plus N plus junction. This is N plus, this green color rectangular box is N plus, and this is my channel stop implant. This is channel stop implant. So they are making another PN junction, P plus N plus PN junction. Yes or no? So this we call it as a side wall capacitance. This we call it as P side, C side wall, which will be, over here written as, see this, side wall capacitance is side wall as CSWJ into P. Now what is P? Total parameter length around the N plus region. Okay. So what is the parameter length over here? This is the same diagram. It's the same diagram. These are side wall. 2, 3 and 4 are my side walls which are surrounded with P plus N plus junctions. So these are side wall. This P plus N plus junction is my side wall. So side wall we don't have an area. We have perimeter. So what is my perimeter? Can you tell me what will be the perimeter of this 2, 3 and 4 rectangle? So sum of the three sides, right? Sum of the three sides of drain diffusion area is my perimeter. So what is my perimeter? Can you tell me? So perimeter will be this. This is my perimeter, right? All the three sides, 1, 2 and 3. Tell me what it is. Count and tell me.
Y plus xj plus w.
Y plus
Y plus w
plus
plus x
plus Y.
plus x. Yeah, y.
This is Y, W, this is Y. So perimeter is 2Y plus W, agree?
Yes.
Yeah. So my sidewall capacitance is C sidewall is CSJW into P. Okay, that's why the unit of a sidewall capacitance is farad per centimeter and not farad per centimeter square, because it's not an area, it's a perimeter. So the total perimeter around N plus region is given by 2Y plus W. Now since source and drain are symmetric, both the perimeter area on the source and drain side will be same. Agree? Yeah? Yes or no? The perimeter?
Yes.
Okay, fine. Now, the junction labeled as here, let's come back to over here. The junction labeled as, let me highlight over here, 1 and 5. They are making a PN junction with what? They are making a PN junction with P silicon substrate and N plus layer. Okay, so this is P silicon substrate and N plus. So this 1 and 5, this is bottom, this is on the left hand side and this is the bottom plate. They are making the PN junction with P N plus. So this is 1 and 5. Okay, so junction labeled 1, junction labeled as 1 is facing the N channel, and the bottom junction 5 is facing the P type substrate. Yes or no? I repeat, junction labeled as 1, What is that junction? P n plus junction is forming the as is facing the n channel, and the bottom junction phi is facing the p type substrate. Yes or no? So what will be the bottom capacitance? We can write it as what will be so it is facing like this. See, bottom capacitance is like this. So we have now 1 and 5. 1 and 5. The 1 is side wall, it is side wall, and 5 is bottom. So can you tell me what will be the area of the bottom capacitance? Area will be length into width, right? So what will be this area of this bottom capacitance? Phi.
So W times Xj.
No. W into Y, na? Length into width.
Ah, right, right.
Area of the rectangle will be length into width, na? This is W. This is W. This is W. This is Y. This is Y. Length into width. So area. So area will be length into width, and the C bottom capacitance will be Cj of 0. Cj 0 into Y into W into Y, farad per centimeter square. So please write down these formulas. C sidewall is CSWJ into P. Now why we have not written DWJ? Because normally if I check here, if I go over here, normally in any PN junction, source voltage is almost like not changing at all. Yes or no? So all the voltages VGS. So let me just open this PDF again. It's fluctuating. Yeah, let me just do it one time quickly. Yeah. So normally we all the voltages are measured with respect to source terminal. So let's say VGS is 2 volt. Okay, I have to enter it over here. So VGS is 2 volt. This is VG minus VS. VDS is 5 volt. So all the voltages are measured with respect to source. Okay. So source terminal is normally constant. It's not changing much. Drain terminal is one it is changing much, and gate terminal is the one which is changing much. Are you understanding? Because VGS is VG minus VS. VDS is VD minus VS. VS voltage is 0. VS voltage is 0. VG voltage is 2 volt. VD voltage is 5. So source terminal is normally containing almost like a static voltage. I mean the voltage is not changing much. At the drain end of the terminal, the voltage is changing much. That is, the switching is happening at the drain. At the source is rarely, fairly quiet. All right. So that's why we have written over here. Write down please this formula. C sidewall is equal to CSWJ into P, where P is 2Y plus W. Where it came from? It came from over here. Okay. Agree? And C bottom capacitance is given by Cj0. Cj0 into area. So the unit will be farad actually. We will not write it as farad per centimeter square. C bottom capacitance will be Cj0 into W into Y, where actually Cj0 itself is farad per centimeter square. Okay. Yeah. Everyone.
Yes, sir.
Okay. Written the formula where area is W into Y. Now we are coming to the end. Just 2 minutes. Just 2-3 minutes. We are coming to the end of the derivation. I know it's a very crucial thing. That's why we are discussing now this again and again. Now let's come back to this. Junction 2, 3 and 4 are all P n plus P n plus P plus junction, right? Because they are making the junction with the channel stop implant. Yes or no? So what is the area? These are all area capacitances, right? Because area junction. So what is the area of junction number 2? Y into xj, correct? Junction number 3, W into xj. And what is the area of 4? Y into xj. Do you agree?
Yes, sir.
Because 2, 3 and 4 junctions are n plus p plus, and your area is y into xj, w into xj, y into xj. Okay. Now we talk about 1 and 5. So tell me, one is again a side wall. So which type of junction we are having over here? P plus, sorry, P n plus junction, because it is forming with the junction over here is P silicon substrate. So n plus, and here it is for one, it is n channel. So again your substrate will be P silicon substrate. So what is the area of one? W into xj, and what is the area for the phi? W into y. Okay, agree? So this table is important of this junctions 2, 3 and 4 and 1 and 5. So please write it down in your books. Junction along with the area and the type of PN junction, and you mark here everywhere. This is 1, 2, 3, 4 and 5. So this is 1, 2, 3, 4, and this bottom one is 5. Understanding this geometry of this rectangle and writing the formulas is extremely crucial. Okay, and remember that the junction capacitance will increase with the channel width. So if I increase my channel width, my junction capacitance associated with the channel width increases, because we have W everywhere mostly. So mostly your capacitance will increase if you increase width of the channel, and that's a very important aspect. So please complete this table: junction, area, type of the PN junction, and the diagram, this diagram. So out of this, which are the side wall? Is this the side wall 2? Yes. Is 3 a side wall? Yes. Is 4 a side wall? Yes. And what is the bottom capacitance? Only 5. Okay, this 5 is the bottom one. Agree? So please write down the table. Completed the table? Everyone? Yes or no? Is the table completed?
Yes.
Okay. Now tell me the doping of the sidewall capacitance and area capacitance should be same or different, because here we have P plus N plus and here we have P N plus. So for sidewall the doping will be different, right? It's P plus junction only. Here it is P plus, here it is P. So here the sidewall junction capacitance have different doping. So sidewall junction capacitance have a doping of Na sidewall, indicating that is sidewall. P plus channel stop implant doping density is Na sidewall, NaSW. It's other than the junction capacitance doping, which is Na. So Na is the doping of P silicon substrate, and Na sidewall is the doping of P plus channel stop implant. So this you take care. So in our entire formula from figure number A, B and D, the sidewall of a typical N plus source and drain regions are surrounded by P plus channel stop implant. Very very important. With a higher doping density than your substrate doping. Meaning P silicon doping is, let's say, Na, it's around 10 raised to 16 per centimeter cube, whereas your P plus channel stop implant doping is Na side wall, which is in the range of 10 raised to 18 per centimeter square. So 100 times more, almost 10 times or 100 times more. So whatever formula we have derived, we have to write it in terms of what is Cj0? Zero bias junction capacitance. So sidewall capacitance formula will be different slightly, because the doping is different. Only this is different, right? Na is different over here, so the formula will be different. So Cj of sidewall will be the same formula. Only thing is we write doping as Na sidewall. That's it. Only this is the change. So Na NaSW is the sidewall doping density of the channel N plus P plus channel stop implant. Alright. So sidewall zero capacitance, zero bias capacitance Cj0, and sidewall voltage equivalence factor K equivalent of sidewall different will be different from the bottom junction. Alright. So yeah, so phi sidewall is the built-in potential of the sidewall junction. Okay. So here all the sidewalls in n plus diffusion structure have the same depth, right? Yes or no? Xj. See this? All the sidewalls, which are the sidewalls 1, 2, 3 and 4, have a same junction depth Cj. Yes or no? Sorry, Xj. So we can write over here CSJ will be Cj0 Sj into Xj. Okay, for sidewall junction capacitance will be, so sidewall capacitance will be given by Cj, SWJ will be given by Cj0 SW into Xj. Okay, so Cj0 has a unit how much? Farad per centimeter square, and Xj has a unit what? Centimeter. So what is the unit of sidewall capacitance? Farad per centimeter. Got it? So this you take care. Whereas sidewall voltage equivalence factor K equivalent sidewall will be given by this formula. So what will be different? The built-in potential will be different over here. Okay. So all this you will understand it more when we solve a numerical. So is this clear now, everyone? I know it's a difficult topic, but we have to cover it somehow. I hope it is better now. So why it is Xj we have understood? Because of the depth. Because of the depth of the junction, Xj is the same. So it is 1, 2, 3 and 4 facing junctions which are having depth Xj. So that's why we have a perimeter over here, not area. So it will be Cj0 SW, which is sidewall, into Xj, and K equivalent sidewall. So this completes the derivation. Now the main thing is, how do we decide the area capacitance and the periphery or sidewall capacitance? How do we decide? Tell me. So we go back to this PDF. We have written all these four capacitances. Now we are ready to write the formula. So what are the area capacitance? C, D, B, J, C, S, B, J. These are area capacitance, right? Now I know all the terms. So this will be given by, because drain terminal is changing a lot, right? The voltages are changing a lot. So the K equivalent factor will come over here. So it will be K equivalent. Okay, K equivalent is a function of voltage, definitely, multiplied by area multiplied by Cj0. Yes, because this is dimensionless, multiplied by area multiplied by Cj0. Why I am writing area? Because the area we are talking about, which junction we are talking about, 1, 2, 3, 4, we don't know. So all of them we have written a table, right? Which area is different for them. So this will be unit will be farad. Understood this? K equivalent Cj0A. So this will be given by, we have written that, right? Here it is. K equivalent A into Cj0, right? K equivalent A into Cj0. Now what about, this is drain to substrate junction capacitance. What about source to substrate junction capacitance? I told you, the source region is remaining quiet, the voltages there are not changing much. So what it will be given by? Area into Cj0. The K equivalent term will not be present. Okay, since the switching doesn't happen at the source end, it happens at the drain end, and that is given by farad again. So we know the formula for Cj0, we know the formula for K equivalent. We can write down the formula for drain to substrate junction capacitance, source to substrate junction capacitance. Okay, now CSWDJ, CSWSJ, drain to substrate sidewall capacitance, source to substrate sidewall capacitance. So these are called as periphery capacitance or sidewall capacitance. whose unit will be farad. Again, the unit will be farad over here, but tell me, what will be the formula? Same, right? It will be K equivalent for SW, right? For sidewall. The sidewall doping is different. That's it. So this will be SW. Will it be A or P? Instead of A, will we have a P? Yes or no? Tell me. It will be sidewall. Will it be A or P? Here it will be P. Okay. And here also instead of area we have a perimeter, right? So this also will be CJ0 sidewalls. Got it? Yes, so side CJ0 unit is farad per centimeter square. Perimeter is centimeter. We can check. And so this unit will be farad per centimeter. So we'll check it out. Okay, so this are the, please write down these formulas. K equivalent sidewall is the doping is different of the channel stop implant. And CJ0 also doping is different for the channel stop implant. Okay, you have written these formulas where A is the junction area and P is the perimeter of sidewall junction. So I have completed, we have completed the MOSFET capacitance derivation as much as detail and possible. Now can we go for the numerical part? Everyone?